8.4. Changes in mechanical energy for non-conservative forces. The outline of this video is as follows. We will discuss the energy equation for systems that include non-conservative forces. We will then apply this concept by working through several detailed examples. This includes example 8.7, which involves a crate sliding down a ramp with friction. Next, we will look at example 8.8, analyzing a block spring collision both with and without friction. We will follow this with example 8.9, which examines a more complex system of connected blocks, friction, and a spring. Finally, we will learn how to interpret energy bar charts in conceptual example 8.10. This slide introduces our key equation for systems with non-conservative forces, like kinetic friction. When friction is present, mechanical energy, which is the sum of kinetic and potential energy, is not conserved. This is because friction does work and transforms that mechanical energy into internal energy, which you might observe as heat. For an isolated system, we can write a more general conservation of energy equation: the change in kinetic energy, delta K, plus the change in total potential energy, delta U, plus the change in internal energy, delta E internal, must equal 0. The change in potential energy, delta U, includes all forms, such as gravitational and elastic. The change in internal energy created by a friction force, F sub k, acting over a distance d, is simply delta E internal equals F sub k times d. The key takeaway is that total energy is still conserved if we account for the internal energy. Let us apply this to our first problem. Example 8.7. We need to find the speed of a crate at the bottom of a ramp. The problem gives us a 3.00 kilogram crate that starts from rest. It slides 1.00 meter down a ramp that is inclined at 30.0 degrees. Crucially, it experiences a constant non-conservative friction force of 5.00 newtons. Our goal for part A is to find the speed of the crate when it reaches the bottom. To solve this, we will define our isolated system as the crate, the surface of the ramp, and the earth. This system involves both a change in gravitational potential energy and a non-conservative friction force, so we must use our full energy equation. Here's the solution for part A. We start with our conservation of energy equation. Delta K plus delta U plus delta E internal equals 0. We first define our initial and final states. Initially, the crate is at rest, so K initial is 0. Its initial potential energy, U initial, is m times g times y initial, where the initial height y initial is 1.00 meter times the sine of 30.0 degrees, which is 0.500 meters. In the final state at the bottom, the kinetic energy, K final, is 1/2 m versus final squared, and we set the potential energy, U final, to 0. The change in internal energy, delta E internal, is the friction force times the distance, or 5.00 newtons times 1.00 meter, which equals 5.00 joules. We substitute these terms into our equation and solve for the final velocity, v final. This gives us the square root of the quantity 2 divided by m times the quantity mgy initial minus fkd. Plugging in our numbers gives a final speed of 2.54 meters per second. Now let us look at part B of the same example. The goal here is to find how far the crate will slide on the horizontal floor, assuming the friction force remains 5.00 newtons. We can solve this very efficiently by analyzing the entire motion in one step. We will set our initial state as the crate at rest at the top of the ramp, and our final state as the crate at rest on the floor. In this new analysis, the initial kinetic energy K initial is 0, and the final kinetic energy K final is also 0, because the crate starts and ends at rest. Therefore, the total change in kinetic energy, delta K, is 0. The initial potential energy is still U initial equals mgy initial, and the final potential energy, U final, is 0. This means the total change in potential energy, delta U, is negative mgy initial, which is negative 14.7 joules. Continuing with the solution for part B, the only remaining term is the change in internal energy, delta E internal. This is equal to the friction force, F sub k, times the total distance slid, d total, which includes both the ramp and the floor. Our energy equation, delta k plus delta U plus delta E internal equals 0, simplifies. Since delta k is 0, we have negative mgy initial plus F sub k times d total equals 0. This tells us that all the initial gravitational potential energy is transformed into internal energy by friction. Solving for d total, we get mgy initial divided by F sub k, which is 2.94 meters. Since the ramp was 1.00 meter long, the crate must slide 1.94 meters on the floor. The slide also includes a what-if scenario. If the ramp angle is reduced, the ramp becomes longer. This means friction acts over a greater distance, transforming more energy, and the crate's speed at the bottom is lower. In our next example, 8.8, we analyze a block spring collision. The problem setup involves a 0.80 kilogram block given an initial velocity of 1.2 meters per second. This block then collides with a spring that has a spring constant, K, of 50 newtons per meter. Part A of this problem makes a key assumption. The surface is frictionless. Our goal is to find the maximum compression of the spring, which we call X max. For this part, our system is just the block and the spring, because there are no non-conservative forces like friction acting. This is an isolated system, and we can say that mechanical energy is conserved. This means the change in kinetic energy plus the change in potential energy must equal 0. Here is the solution for the frictionless case in part A. We apply the conservation of mechanical energy, delta K plus delta U equals 0. Let us define our states. The initial state is when the block is moving at velocity versus sub A, just before it hits the unstretched spring. Here, the initial kinetic energy is 1/2 m's versus A squared, and the initial potential energy is 0. The final state is when the spring is at its maximum compression, X max. A sit, this exact moment. The block is momentarily at rest, so the final kinetic energy is 0. All the energy is now stored in the spring as potential energy, so U final is 1/2 kx max squared. Substituting these into our conservation equation gives the quantity 0 minus 1/2 m versus A squared, plus the quantity 1/2 kx max squared minus 0 equals 0. This simplifies to 1/2 k x max squared equals 1/2 m versus A squared. We are solving for x max, which is 0.15 meters. Now for part B, we introduce a non-conservative force. We want to find the maximum compression, X sub c, if there is a constant kinetic friction force with a coefficient mu sub k equal to 0.50. Because friction is present, mechanical energy is not conserved. We must now include the surface in our system, making our system the block, the surface, and the spring. We have to use our full energy equation, delta K plus delta U plus delta E internal equals 0. The friction force, F sub K, is equal to mu sub K times the normal force, which on a horizontal surface is mu sub K times m times g. As the block compresses the spring by a distance x sub c, this friction force does work, transforming energy into internal energy. The change in internal energy, delta E internal, is therefore F sub k times x sub c, or mu sub k times m times g times x sub c. To solve part B, we again define our initial and final states. They are the same as in part A. Initially, K initial is 1/2 m versus a squared, and U initial is 0. In the final state, K final is 0, and U final is 1/2 kx sub c squared. But now we also have the change in internal energy, delta E internal, which is mu sub k mgx sub c. We substitute all three of these changes into our full energy equation. This gives us the quantity 0 minus 1/2 m versus a squared, plus the quantity 1/2 kx sub c squared minus 0, plus mu sub k mg x sub c, all equal to 0. If we rearrange this, we get a quadratic equation for x sub c. We have a term with x sub c squared, a term with x sub c, and a constant term. Solving this quadratic equation gives a physically meaningful positive root of x sub c equals 0.092 meters. As we expected, this is less than the 0.15 meters from the frictionless case, because some of the initial kinetic energy was transformed by friction. Example 8.9 presents our most complex system yet. We have two blocks, M1 and M2, connected by a string over a pulley. Block M1 is on a horizontal surface, is attached to a spring, and experiences friction. Block M2 is hanging vertically. This system combines multiple energy types. The setup is that the system is released from rest at the exact moment the spring is unstretched. We are interested in the point where the hanging block, M2, falls a distance inf, and the entire system momentarily comes to rest again. Our goal is to use this information to find the coefficient of kinetic friction, mu sub k, between block M1 and the surface. To solve this, we must first define our system. To account for all energy changes, our isolated system must include both blocks, the spring, the surface, and the earth. This system has a non-conservative force, friction, and two types of potential energy, gravitational and elastic. Therefore, we must use the full energy equation, written as delta K plus delta U sub G plus delta U sub S plus delta E internal equals 0. We will analyze the energy change from the initial state, at rest, with H equals 0, to the final state, also at rest, after M2 has fallen a distance h. Because the system starts at rest and ends at rest, the initial kinetic energy and final kinetic energy are both 0. This means the total change in kinetic energy, delta K, is 0. Now let us find the other three energy changes. First, the change in gravitational potential energy, delta U sub G. Only block EC2 changes height. We set its final height as y final equals 0, which means its initial height was y initial equals h. The change, final minus initial, is therefore 0 minus m 2 grams h. Second, the change in elastic potential energy, delta U sub S. The spring was initially unstretched, so U initial is 0. As M2 falls by h, M1 moves a distance h, stretching the spring. The final elastic potential energy is 1/2 kh squared. The change is 1/2 kh squared minus 0. Finally, the change in internal energy, delta E internal. This is caused by friction acting on block M1 over the distance h. This change is F sub k times h, which is equal to mu sub k times the normal force times h, or mu sub k m1 gram h. This slide shows the final result of our analysis. We take all the energy changes we just found and substitute them into our main equation, delta k plus delta u sub g plus delta u sub s plus delta E internal equals 0. This gives us 0 for delta k plus negative m2 grams h for delta u sub g plus 1/2 kh squared for delta u sub s plus mu sub km 1 gram h for delta E internal, all summing to 0. Our goal was to find the coefficient of kinetic friction, mu sub k. We can now rearrange this equation to solve for it. We move the terms to get mu sub km 1 gram h equals m2 grams h minus 1/2 kh squared. Assuming h is not 0, we can divide the entire equation by h. This gives our final expression. Mu sub k equals the quantity m2 grams minus 1/2 kh, all divided by m1 gram. In this conceptual example, we will interpret energy bar charts. These charts show the energy distribution for the system from example 8.9 at 3 different moments. Let us look at chart A. We can see that the bars for kinetic energy, K, elastic potential energy, U sub S, and internal energy, E internal, are all at 0. The only energy present in the system at this instant is gravitational potential energy, Ni U sub G. What configuration does this represent? Since the kinetic energy is 0, the system must be at rest. Since the elastic and internal energies are 0, the spring must be unstretched, and no friction has occurred yet. This corresponds exactly to the initial configuration of the system, at the moment it is released from rest at its highest point. Now let us analyze the other 2 charts. In chart B, we see that all 4 types of energy are present at the same time. The system has kinetic energy, so it must be in motion. It also has gravitational and elastic potential energy, as well as some internal energy from friction. The bar for U sub G is at 50%, which indicates that the hanging block, M2, has fallen halfway. This chart represents the system while it is in motion, partway through its descent. Finally, look at chart C. Here, the kinetic energy is 0 again, and the gravitational potential energy is also 0. This means the system is momentarily at rest, and the hanging block has reached its lowest point, y equals 0. All the initial potential energy has been transformed into either elastic potential energy, EU sub S, or internal energy, E internal, which are both at their maximum values for this process. Let us summarize the key points of this section. The main takeaway is that when non-conservative forces like friction are present, mechanical energy, the sum of K and U, is not conserved. This is because the work done by these forces transforms mechanical energy into internal energy, which we call delta E internal. However, for a fully isolated system, the total energy is always conserved. We can express this with our general conservation of energy equation. The change in kinetic energy, delta K, plus the change in total potential energy, delta U, plus the change in internal energy, delta E internal, equals 0. It is important to remember that the delta U term must include all forms of potential energy in the system, such as gravitational and elastic. The change in internal energy from kinetic friction is calculated as F sub k times d, where d is the distance over which the friction force acts. This final slide presents a couple of review questions to help you check your understanding. The first question refers back to example 8.8 part B. the block spring collision with friction. We solved a quadratic equation to find the compression, x sub c. Why was the positive root the only physically meaningful one? What would the negative root imply in that situation? The second question is about Example 8.7, the crate on the ramp. We found the crate's speed at the bottom was 2.54 meters per second. The question asks, if the horizontal floor in part B had been frictionless, what would the crate's speed be after it had slid 1.94 meters on that floor? Think about these, and we can discuss them.